Okay, we're going to cover the basal ganglia because last winter we covered it in quite detail in several different episodes. And this is where movements happen. So there's a lot of humans are constantly doing movements and actions. This is action. So the episodes we covered with the basal ganglia is episode 48, autism in the basal ganglia, motivations, and movements from learning and habits. Episode 49, autism and Parkinson's. Parkinson's is a hot spot right here, especially here, here, and here. We probably won't cover much on Parkinson's in this whiteboard, but we will later, I promise you. Episode 50, autism in the basal ganglia. Repetition, sameness, and habits. And also episode 47. We could include episode 47 here, the autistic phenotype and how internal calculators shape our preference. We talk about internal calculators a lot, and they should be talked about. So these two, specifically, basal ganglia, we're going to talk about the basal ganglia. This is one side of the basal ganglia. They're just spots right now, but we're going to get through it. Okay? The basal ganglia is essentially 5 subcortical areas. Okay? There's input areas, and this is called the dorsal striatum. Input areas. Marker's going out already. The dorsal striatum is 2 areas. The caudate nucleus and the putamen sometimes. So these 2 areas receive the inputs. And then there are also relays. Relays are globus, pallidus, external, and subthalamic nucleus. Globus pallidus are these 2. They almost make a triangle. But the external, because this is going to be center, and then we'll draw out the contralateral here in a minute. So this is globus pallidus external, and this is the subthalamic nucleus. This is the thalamus. The subthalamic nucleus is just basically another assistant for the thalamus. The thalamus is a workhorse, and it needs help. And then the output areas in blue. Globus pallidus internal and substantia nigra, pars, reticulata. These 2 nuclei are very identical. Globus pallidus internal here, because it's internal, medial, and the substantia nigra, pars reticulata. This is the substantia nigra. This is in the midbrain, the mesencephalon. So if we were to look at it, it would look more like this, flat, looking at it from this posterior end. But I had to rotate it up so we could see the reticulata, which is here, and then the pars compacta, which is, so reticulata, pars compacta. They have different roles. We're going to get through it. These 5 subcortical areas orchestrate our movements. Every movement, besides those funky reflexes that we have. If we hit an elbow or a knee, when the doctor taps our knee with the little spike hammer like thing, and it goes. Every movement is orchestrated here. So this is why it's important. So we have the input areas, and I'll just go ahead and draw out contralateral because we're going to do the go side. That's a good point here. This is go, no go. This is go, no go. This is orchestrating movements and suppressing movements. So I'll just draw this out contralateral. Remember, ipsilateral is one side. Contralateral is both sides. So we have the caudate nucleus here and the putamen. These are the inputs. We're going to make sense of what the inputs mean. And then we have the globus pallidus external on one side. A little relay station. It has hidden roles. We're going to dissect these hidden roles for sure because it's missed. It's new. Textbooks don't teach it. And then the subthalamic nucleus, just a little flat spot right below the thalamus. And we have the thalamus. The thalamus is the target. Remember, it's a workhorse. And the pars reticulata, the globus pallidus internal. So why is the thalamus blue, the same as the outputs? This is the target. This orchestrates everything. It's a sensory relay station. It receives all sensations. And then it's also on that feed-forward feedback loop. Remember the mini columns. Everything is orchestrated through the thalamus. And then the substantia nigra pars compacta is also involved. We're gonna understand why. This is a modulator. So we could add modulator. The biggest one, substantia nigra pars compacta. SNC, you can see that abbreviated as SNC, and reticulata is SNR, lowercase. The C and R are lowercase. This is the basal ganglia. So what does it mean? Just real general, we'll map out the go side here and the no-go side here, because these have distinct names. Direct pathway equals go. Okay, so inputs, excitatory projections come in to the caudate nucleus and the putamen, and these orchestrate our movements. These are conductors. They're recruiting, activating, and turning off, inactivating. Downstream regions. For the go side, simple. Projections come in, excitatory, from the cortex. We're going to map these out because this is going to sound too simple. The dorsal striatum of the caudate and putamen will send inhibition. Everything coming out of the dorsal striatum is inhibitory. You know about autism and the lack of inhibitory, or a problem with the inhibitory. So it will inhibit the globus pallidus internal and the pars reticulata. That will in turn, while shutting these off, allow them to, it will feed up to the thalamus, and that frees up the thalamus to send projections back up. Remember, layer 4 of the mini columns. If we have these mini columns, right? Remember, we can just map these out like this. We have the cells, the collection of different cells here, and then we have the stellate cells in layer 4, and then we have more cells down through layers 5 and 6. Remember, 5 is about firing, 5A is tonic, 5B is burst firing. Then layer 6 has A and B as well. Cortical thalamo, so it speaks back to the thalamus. And 6B is cortico to cortical, speaking throughout the cortex. So there's a 5A and 5B based off of the firing. And 6, where is it going? Remember, down below 6 is a lot of white matter tracks. Okay, so remember you have these cells here. And also this is where the spindle neurons are in some of the areas. Spindle neurons are a little flat and funky looking, but these are loaded with cells through here. Whenever the thalamus is freed up, so let's go back. Excitatory inputs hit the caudate and putamen, and we'll just discriminate those in a minute. And that will inhibit the globus pallidus internal and the pars reticulata, substantia nigra pars reticulata, and that frees up the thalamus. Inhibit the thalamus anymore. So the thalamus will speak back up to, you know where, layer 4. This is where the inputs come in on the mini columns. Then it goes to layer 2 and 3, because this is where we live. This is where our intelligence lives, our memory, our experiences, our ability, and so forth. And then 2 to 3 will speak back down to 5 and 6. How much intensity does it want to send? And then where is it going? That's the mini column. This is pretty much the function here. Every movement that we're making is orchestrated through that. Sounds simple. This is the indirect pathway. No go. Stop. Stop. So excitatory inputs come in to the caudate and to the putamen. Okay? And here there's a little bit more going on. The caudate and putamen will send signals to the globus pallidus external, and then this will kind of do a lot of different things, but we'll parse out what this is doing in detail. And this will also speak over to the subthalamic nucleus. The subthalamic nucleus will shut off. Nope, excite. Will excite these. And then that allows these output areas, the globus pallidus internal and the substantia nigra pars reticulata, to go back to the thalamus. It will instruct the thalamus to stop. So you can see there's a little bit more coordination for the stop, for the suppression, and there's timing involved here that we're going to get into. And essentially, that's the direct pathway and the indirect pathway. It seems simple. That's a simplistic way of looking at it. So let's talk about the input areas, because this is going to be huge. What are these? What are those? So the input areas, yeah, that's a good way of thinking about it. Because these are input areas, so what's coming in? So the biggest thing here is the cortex. This is the biggest thing that sends signals excitatory, they're always excitatory, to these areas. The second one is the thalamus. The thalamus will send inputs, projections back to the dorsal striatum. And a lot of this is all excitatory as well, but the thalamus is telling it to pay attention. Something important or unexpected is about to happen. So help be on alert here. Because remember, the thalamus is always asking and needing help. Okay? This will also help provide a little bit of arousal and context to what is happening. Because it's a workhorse. The thalamus is a workhorse. The second thing, or the third thing, is substantia nigra pars compacta. Here, this is a big input area because we're going to talk about the specific cell types, medium spiny neurons here, and make sense of like so-called typicals versus autistics. Substantia nigra pars compacta is dopamine, D1 and D2 dopamine. This is excitatory, and D2 are inhibitory. So it's modulating. It's modulating the attention, the intensity, and so forth. These use DR1 and DR5 receptors. Dopamine receptor 1, dopamine receptor 5. Dopamine only has 5 receptors. R2, 3, and 4. Substantia nigra pars compacta, its major projection, major target, is the dorsal striatum. This is dopamine. We also have the ventral tegmental area for dopamine. So dopamine is very important. This is telling the dorsal striatum that this is good or this is bad. It's providing some value and intensity. It will amplify it if needed. Okay, it's teaching it what is worth doing. Do I want to do this? And so forth. Also, as modulators, to a lesser role, these are the 3 biggest input areas to the caudate and the putamen. But also, there are modulators like serotonin, so the dorsal raphe for serotonin. This is providing some information here to say, have patience, just give it a moment type of thing, okay? That's serotonin. That's what it's doing. So you also know about like the mood thing. So I'm okay right now. In this situation, you're okay. Or no. And then choline. So it's acetylcholine, essentially, but it's not from the forebrain. The nucleus basalis of Menert does not really project to these areas for the choline. We've talked about in the mesencephalon episode that there's also little regions down in the brainstem, the mesencephalon, that releases choline. Remember the Edinger-Westphal nuclei that's heavily involved with cranial nerve 3 as well. There's little subdivisions down here that also release choline, and this is one of them. They're very long and complicated nomenclature, but P, G, L, T, D, and so forth. This is helping shift between focus and attention. It's helping provide a little bit of flexibility. Pay attention to this type of thing. That's what acetylcholine does. And then even less than these two are things like from the limbic areas, like the amygdala and hippocampi. So most of these are excitatory, but there's an unknown role with the globus pallidus external that's speaking back up to the dorsal striatum. We're going to get there in a minute, but for now, we need to understand the signals coming in from the cortex, because that determines everything. So let's just map this out from a side view. And I will use just one color for all the subcortical areas. If we're looking at this from the side, let's say the thalamus is here. Now there's a reason I'm not going to color all of this in, because the thalamus is very midline. It's very medial. So we're going to have to work out this way. We're going to have to work out this way. And you can see there's a lot of overlap. So it's going to be hard to map this out laterally. If we're looking at it like this way. These are lateral. So yeah, it's going to be hard now for me to draw this out. But the caudate is long. It has a tail. It even wraps around and connects kind of to the amygdala. So this is, it's like a shrimp. It reminds me of a shrimp. So this is here. Now it just depends on how deep you want to go. If you're looking at it from behind, is how much this is going to show up and which part. Because if you're looking at it from this way, you'll be able to see different parts of it. It's going to look bigger. But the putamen is right here. And these are connected just briefly. So caudate nucleus, putamen, thalamus right here. So if you notice, the putamen is going to block the globus pallidus. So the globus pallidus would sit just right here. Okay, this isn't as important. So this is the thalamus. Subthalamic would sit about right here. And then the reticulata and compacta would be down here. Remember, we drew out the brainstem. If you're looking at the brainstem like this, if you just want to slice it open, that way you can see the pars reticulata and compacta are in the kind of anterior part of the mesencephalon. So if it's like this, if the brainstem, remember, if we have the pons, the little football shape, and then the brainstem goes down. So mesencephalon, it would be like here, superior colliculus, inferior colliculus, so substantia nigra compacta and reticulata here. And then we would have the cerebellum like this. Cerebellum's going to have a role, motor movements, fine tuning. It's going to have a role. We might get into it. So the cortex here would be all of this area. All right, so the occipital lobe, parietal, the sensory motor, which is here, parietal is back through here, and then the frontal cortex, the prefrontal cortex. Okay, so the major part coming into here is the sensory motor area, which is essentially here. Remember, we have things like the somatosensory cortex here, and then the sensory motor here. We have the frontal eye fields are up here. Frontal eye fields, sensory motor. There's a lot of habits living up through here. Okay. And then we have the somatosensory. This is a large part. This is probably the second most inputs coming in. This is probably the most inputs. Remember, we love to build habits and store them up through here. We love repetition and habits. This is who we are. This is why we're covering this. And then some prefrontal areas. Remember the dorsal striatum. No, the dorsal lateral prefrontal cortex up through here. this area of the prefrontal cortex right through here, okay? And then the orbital frontal cortex right through here, right here. This is good with working memory and providing a plan. So it will project down through here to kind of give it some instructions on what to do based off of this, what we're encountering. The orbital prefrontal cortex here, remember, is mostly sensory. It has a lot of specificity of what the living organism wants and kind of desires in real time. It's providing value and reward. Is this worth it or not? With the specificity, if you want, let's say, if you're thinking that you need caffeine, the orbital frontal cortex is going to tell you exactly the source of the caffeine that you want. Maybe I want coffee. Maybe I don't want coffee. Maybe I want tea or whatever. That's going to help this out. And then the medial prefrontal cortex is in through here. Remember, the ACC is here. And then the insula would live right through here, the anterior insula. Not involved, though. This is involved. This is involved because this is a big calculator. This is conflict monitoring and evaluating risk reward. So it's providing constant updates. This isn't just a one-time thing and you're done. This is constant. These two networks are dancing around constant. There are so many. This is a lot of electrical activity and projections right here. And it will also allow it to update because you're evaluating reward and the environment. Okay, that action didn't give me what I wanted. I have to do something else. The ACC will help conduct that, adjust your behavior. Also doing the conflict monitoring and so forth. And then the parietal lobe is back here. Remember? So if this is the occipital, and then the parietal, see, we're just building the brain here. And the temporal lobe will run through here. So we're just mapping out the brain here. The parietal lobe will also send some inputs through here. And it's going to be, because the parietal is sensory integration a lot, it's providing some context-dependent cues. Okay, look here or don't look here. What was that noise type of thing? That noise got loud and so forth. So it will help orchestrate movements here. So these are the biggest cortex inputs coming in. So what does that mean? We are all different. This conversation today is based off of who we are, what we do, what we like, and so forth. This is why we're so different. So let's just really zoom in here because this is getting way too long. Let's just zoom in here, okay? And let's just extract a single cell from one of these two areas, okay? First thing I want to say, though, is the more medial you are in these subcortical areas, and even in the cortex, more likely it is something new, novel, or goal-directed. And then habits will live outward, lateral. So the putamen is more about habits. So it receives a lot more inputs from that sensory motor area because we love to send our information and our abilities to this area. So more goal-directed through here, habits go lateral. And if you think about the evolution of the living organism and humanity, it makes sense because we had to have motivation to do and get what we want first. And then we can shift those over. And I think that frees up space for the goal-directed behavior. We can all understand that change is hard because we're going to talk about morphology and these synaptic connections. So let's just extract a single cell. I'm just picking one. It's just a general example. Because these are medium spiny neurons. So we have the cell body, the nucleus, okay? So let's just say this is a cell. Be it good or a bad drawing, I don't know. The cells in the dorsal striatum are very special. They're called medium spiny neurons, MSN. And that's why the dopamine is a big part of this with the D1, D2. So if you think about this, these are like branches or limbs off of a tree. And then these are dendrites, okay? And then they have little spines on them, okay? All of these spines are little parking spots. The projections coming in from those other areas that we drew out in the cortex, or wherever it might be, will land on a specific spine. Okay, now with the medium spiny neurons, spines are bigger. They're just a little bit larger than normal cells. So they will look more, if you look at a tree, okay, this is an easy example. Some trees are loaded with leaves and some are not. Okay, these medium spiny ones are like a nice oak tree in the summer. Okay, now let's really zoom in again. So let's look at this one. Let's look at this branch, this dendrite, and then this spine right here. Let's just say this is the spine, okay? This specific spine will receive a specific projection coming in, and it will mean the same thing every time. The thing that connects to this, that sends a projection to the spine, will be the same. Okay, so we have the presynaptic, the cleft, and the postsynaptic. Okay, this connection here will mean the exact same thing every time. So it's providing a little bit of update information. So that's what we're talking about, these neural correlates. So let's just say this came in from the sensory motor area and it projected down to the putamen because we're building a habit. And it's hitting this cell, but that specific spine. So this information will come in, signal to this spine, and this cell will know what to do with it and how to help conduct these downstream actions or inactions, which is still inaction, because you're suppressing the target, you're suppressing movement. It's what the living organism is doing. This is why things like motivation, or do you define motivation, or your central nervous system does? Because as these are firing with repetition, these grow. So postsynaptic or presynaptic and postsynaptic, okay? And there's like little parking spots here. Remember, like in MDA and AMPA. AMPA is going to be huge here. It's huge with learning, because this is what we're talking about. As you build repetition and habits, these things get bigger. This is called morphology. It's synaptic plasticity. So let's compare this size. Remember, let's just say the inside diameter here versus something that you don't do very much. You're not very good at, so forth. Maybe you want to be good at it. Maybe you want to, but you just don't have the skill set yet. This in the central nervous system is going to be preferred. The brain does not like to work. The central nervous system does not like to work. It just likes to respond. So when things are larger, like this, that is going to get the privilege. So this cell that is in this nuclei, that means this information will connect and carry out the movement. With the autistic phenotype, these cells are different. These medium spiny neurons are different. Okay, so dendrites are a little bit larger, and the spines have a unique specificity and special privilege. So this information coming in from the cortex will sure fire over anything else, because all of these different flexibilities, you can call these different spines flexibility, that the living organism might have is not there with the autistic phenotype cell. So this certain spine, let's say, is larger like this and just limits flexibility and causes sameness or habits, will always win. This is a big part of the autistic phenotype. This is why, autistic or not, you don't necessarily define motivation. These neurocorrelates and connections do. This is why change is hard. The central nervous system is going to determine what you do. Now, I'm not saying that you can't reverse this. I'm not saying you can't change and build better connections through here. Maybe more connections, maybe strengthen this one up because it's more preferred and these receptors will hit. I'm not saying that at all. But with the autistic phenotype, the dorsal striatum and these sensory input areas and the lack of the prefrontal areas coming into the dorsal striatum are limited. Remember the ACC. We talk a lot about the ACC. That's action selection. Next episode's about the basal ganglia. We'll parse out this area right here, the globus pallidus external, because this is sending updated feedback to the dorsal striatum, and it's not well known. And also the subthalamic nucleus, this little thalamus helper. It's receiving direct inputs from the cortex as well to help providing it some helping the thalamus respond and so forth. But the big takeaway here is the kind of so-called abnormal medium spiny neurons and the limited flexibility with connections coming into the dorsal striatum. Remember, this is just extracted out in one of these nuclei, and then the connections happen. The big takeaway as well is this one spine receives information from one presynaptic area, and that's providing information, and as which each synapses with each connection coming down into from the cortex down to the dorsal striatum, it's building a summary. Each synaptic connection builds summary, and it's building a bigger story overall. And then it gets to the time where it's orchestrating the go or no go movement, which is speaking back up to the cortex. And it's just a constant feedback loop. This is constantly going. I don't know if I covered everything I wanted to cover, though. I do want to say this with the autistic phenotype, because this is a big thing. This is a big thing because you can now know about B2. Insistence on sameness, inflexible adherence to routines, or ritualized patterns of verbal or nonverbal behavior. Speech is heavily involved in here. Speech will run through here. And B3, highly restricted fixated interests that are abnormal in intensity or focus. Strong attachment to or preoccupation with unusual objects. Excessively circumscribed or perseverative interest. This is autism. B3 is the core of autism. Restricted fixated interests that are abnormal in intensity or focus. Right here. We build habits. We have these so-called splinter skills. Asperger's little professors. Because these connections are constantly firing. And it's easy for us to sit here. Remember the sensory processing with the amount of being able to absorb information. That information goes here. We're kind of mapping this out. Basal ganglia. Do you define your motivation or not?